in this procedure, if you assume that this rigid body is pivoted at this point P, let us divide the reaction force on the rigid body as Rx and Ry respectively. When it is subject to gravity at the center of mass, the gravity force acts, that is mg. For the sake of simplicity, let us not include any other external forces except gravity and the reaction force. The components of reaction force are Rx and Ry respectively. The x is the y axis and the center of mass, let move with acceleration along x direction, with x along y direction, let its acceleration be ay, down. If you wish, you can take the x in left hand direction or leftward direction, and I have taken ay down, you can take ay off, that is your choice. According to this assumption of the directions of these vectors, the forces and accelerations, I need to build the equations. Let me assume that angular acceleration be alpha. Remember, you may give alpha in this way. You may give alpha in this way. This does not depend upon the points. This is a general misconception. You might think that it is pivoted about this point. At this point it will rotate. About this point it will rotate. Therefore, alpha should be like this. Like this. You may give alpha like this, or like this, or like this, or like this, or like this, doesn't matter. Since we have taken the center of mass as the reference, you can take alpha in this way. The direction of alpha should remain unchanged for all the cases. So, if you take alpha in this way outside, or alpha in this way inside, or alpha about the center of mass point, or about the pivot, or about any point outside, doesn't matter, because the alpha, the angular velocity, angular acceleration of the rigid object, do not depend upon the reference point. This is the complete free body diagram. In this free body diagram, we have shown the forces, splitting the forces into components along the respective axis, along with the accelerations, linear accelerations component and the angular acceleration. Complete free body diagram comprised of both the force and acceleration. Force equation write first. F is equal to ma along x direction and along y direction. A is the acceleration of the center of mass. The net force in this case is Rx in positive x direction, that is plus, and I have taken x in positive x direction, so you can write x is plus. Without writing the arrow over this lattice, you can write the equation in scalar form, considering the direction as a plus or minus, or plus I cap or minus I cap, plus j cap or minus j cap, Fy. I have taken the reaction force along positive y direction, therefore this is Ry plus m into Ay I have taken in negative y direction, so minus Ay. I have taken the force, gravitational force, that is always downward, we need not assume it, so minus mg. This is the net force acting on the object along y direction. Therefore, mj minus ry can be written as m into ay. Equation number 2, and we can consider this as equation number 1. Then torque equation. This is force equation, means equation for translation. Newton's equation for translation. Torque equation means Newton's equations for rotation. About the center of mass, take the torque and equate it to IC into alpha. In vector form you write first. Since the gravity passes through the center of mass, it cannot produce a torque about the center of mass axis or z axis. Then these two forces will produce a torque about this axis. If the torque about the center of mass axis is assumed to be clockwise, you can write minus tau c k cap. I say is the moment of inertia about the centroidal axis. Alpha we have assumed in clockwise sense, minus alpha k cap. In this way, tau c is equal to IC into alpha. So, two scalar equations, force equation, another scalar equation, torque equation. Then kinematical equations. For kinematical equation, you can write the equations for translation, the equation for rotation. For dynamical equations, we have written the equation for translation and equation for rotation. Dynamical equation means force equation, torque equation. Kinematical equations means the relation between the velocities, linear and angular, the relation between the accelerations, linear and angular, as discussed earlier. So, this is the simplified version, the simplified manner I have written the FBD, the free body diagram, and the force equation, the torque equation, and kinematical equations as we have discussed. Let me present all these through a simple example. Let us assume that this disk of mass m and radius r is placed on a smooth horizontal floor. And a force is acting horizontally whose magnitude is equal to F at the topmost point of the disk, whose center is C. Find the acceleration of the center of mass. Find the angular acceleration of the disk and find the velocity of the center of mass. And you can find the angular acceleration of the disk as the function of time. This is the question. You need to calculate the 4 factors. For this, we need to write the dynamical equation for translation, the dynamical equation for rotation, and the kinematical equations for translation and kinematical equation for rotation. Let us do step by step. Step 1. Is to draw the free body diagram. This disk is experiencing a gravity force. Gravity pulls the disk down, and the gravity force acts at the center of mass of the disk. If it is uniform, unless it is stated, we have to assume that the disk is uniform. For uniform disk, the geometrical center and the center of mass will coincide. Gravity acts at the center of the disk. And at this point, say Q, the disk is touching the horizontal floor. Therefore, this is the tangent. And this is the normal. Along the normal, the floor will push the disk in upward direction. And that is what we call normal reaction offered by the ground. Since the ground is smooth, there is no force acting along the tangential direction. That is the frictional force. Frictional force is a tangential contact force. When either the disk is smooth or ground is smooth. If any one surface is smooth, no friction will come into play. When both the surfaces are smooth, also there is no friction. So frictional force is a tangential contact force. No force is developed along the tangent. Only normal contact force is there. And finally, you have to include the force you are applying from outside. Applied force. This force is called applied force. There is the field force. There is the contact force. This is the field force. This is the reaction. Which reaction? Normal. Reaction or normal contact force. This is the applied force. Under the action of these three forces, the body should move. Let us write the equations. Step number 2. Before we go for the step number 2, in the FBD, let us assume the accelerations. Along x direction, acceleration is x. Along y direction, it doesn't move because it is placed on a rigid horizontal surface. So there is no motion along the y direction or y axis or normal direction. So x is equal to a and ay is equal to 0. And alpha is assumed in this sense, in clockwise sense. Now the step 1, that is the free body diagram, is over. And what is step 2? Write the force equation. What is the net force acting on the object, on the disk, in x direction? Along y direction, let us write. So net force along x direction is equal to mass times the center of mass acceleration along x direction. The net force along x direction acting on the object can be written as the applied force is acting horizontally along positive x direction plus I cap. And there is no such force except the applied force acting on the object along x direction. And the acceleration of the center of mass is assumed along positive x direction, that is x is equal to a I cap. So we can get the scalar equation F equal to m into a, equation number 1. Force equation along y direction, Fy is equal to my, m into ay. What is Fy? Force acting on y direction. We have two forces, normal reaction force and the gravity force. Normal reaction force is acting up, therefore it is mj cap, and gravity is acting down, therefore mg minus j cap is equal to mass times acceleration. Here acceleration is how much? 0, because the center of mass is not moving along y direction. From the physical constraint, the physical diagram or the given data or the given condition, the physical condition, you can understand that the center of mass is not moving vertically or along y direction or along normal direction. Therefore, ay is equal to 0. It gives us n is equal to mg. That is the second equation. So after writing the force equations, let us write torque equation. About the center of mass, the torque is equal to moment of inertia about the center of mass axis into alpha. With respect to the center of mass, you sit and see. Through the center of mass, the gravity force and normal reaction force pass. These two forces pass through the center of mass. Therefore, they cannot produce a torque about the center of mass axis. So net torque is produced by the applied force about the center of mass. about the center of mass, the force F produces a torque that's equal to this distance, that is the radius of the disk, into this force magnitude, and sin theta, this angle is 90 degree, therefore sin theta is 1. So directly we can write the torque produced by the applied force about the center of mass is F into R. In which direction? Clockwise direction, because this is the R vector, this is the F vector. This is R vector, this is F vector. Bring the tails of these two vectors to a point, then you can write R cross F, the direction, the sense of rotation from R to F. From R to F, you have to move the angle. The angle is moving in clockwise sense. Therefore, R cross F is equal to RF sin theta. Theta is equal to 90 degree, and sin 90 degree is equal to 1, and the direction is inward or in negative z direction. So this R is equal to radius of the disk into minus kf. This is the torque about the center of mass axis, minus Fr kf. And the moment of inertia about the z axis, already we have calculated in the last class, that's equal to mr square by 2 to alpha we have assumed in clockwise sense. You can assume anti-clockwise sense. When you assume it in clockwise sense, alpha vector is equal to minus alpha kf. So this will give us alpha is equal to 2f by mr. This is equation number 3. So torque equation is over. Force equations are over. Let us calculate the acceleration of the center of mass. The center of mass has two accelerations, along x direction, along y direction. The final step, this step number 3, is the solution of all equations. From the equation 1, we can write x is equal to f by m. Since we are getting positive result, our assumed direction is correct, that is in this direction. Or we can just write x is equal to f by m I cap. Answer. And what is ay? Using the given condition from the physical situation, if you analyze this point, the center of mass is moving in a straight line along the horizontal line, which is passing through the positive x direction. Since this line is horizontal, there is no question of motion of the center of mass along y direction. So velocity ay is equal to dvy upon dt, or you can just write, since vy is 0, since vy is 0, this factor will be 0. Mathematically, if you want, you can write like that, or by applying the idea, by studying the physical situation, we can understand that this point doesn't move along this direction. Therefore, it has no component of the velocity and acceleration along y direction. Ay is 0, x is this mass. So acceleration of the center of mass is equal to x I cap plus ay j cap is equal to f by m I cap. Answer. Next is to find alpha. From equation 3, we can find alpha as 2f by mr. Since we are getting positive result, our assumed direction is correct, either it is in or along negative z axis or negative z direction or negative z direction. Alpha is equal to minus 2f by mr k cap. Answer. Then I ask you to calculate the velocity as the function of time. Velocity of the center of mass is equal to initial velocity of the center of mass plus axis of the center of mass into t. This is kinematics of translation. Along x direction, along y direction nothing will move. So we can just write like this. Since initially the body was stationary, if initially the body is stationary or assumed to be at rest, initial velocity of the center of mass is 0. Therefore, the final velocity of the center of mass is equal to its acceleration. We have to substitute, that is f by m into t. Answer. This velocity as the function of time. Next, angular velocity is equal to initial angular velocity plus alpha t. This vector equation, but without writing the arrow, you can write, or if you want you can put the arrows also. Omega, let us assume that after some time it will pick up an angular speed in clockwise direction. So you can just write minus omega k cap. Since the body, if we assume that initial omega is 0, initial speed is 0, if we assume like this, then this factor will vanish. Alpha we have assumed in which direction? Along negative z direction into t. This gives us omega is equal to alpha t. And what is alpha? Just substitute. We have calculated alpha is equal to 2f by its magnitude. So you have to put the magnitude portion, 2f by mr into t. Answer. And this is a dummy equation, because we do not need this equation. Even then you have to write it, or they may ask you in the fifth step, the fifth question, they may ask you to find the normal reaction. That's equal to mg. Answer. Well, so let us take, let us take another example. This is a rod of mass m, and length L. Let it be pivoted at one of its end, that is P. Assuming that there is no friction at this point. So this is called smooth pivot. and it is subject to gravitational field. How to calculate? The acceleration of the rod acceleration means angular acceleration and linear acceleration. But if nothing is mentioned, acceleration may mean linear acceleration. And we can also calculate the angular acceleration. Of the rod. Furthermore, at the given position, you can also calculate the reaction force offered by the pivot onto the rod. Reaction force offered by the pivot on the rod, and the rod is uniform. So we have to follow the steps of general procedure. Step 1, draw the free body diagram by mentioning all the forces acting on the rod, the field forces, the contact forces. Second, we have to mention the angular acceleration and the acceleration of the rod along x direction, along y direction. Then in the second step, we can write force equation along x direction, force equation along y direction, and torque equation about the center of mass of the rod. So when you are solving step 1, draw the rod, consider the field force, that is the gravity. Since it is uniform, the center of mass of the rod is located at the midpoint of the rod because it is uniform. The length of the rod is given as L. At this pivot, we have a normal reaction, we have another reaction force along the horizontal direction. We can call it Rx. Along normal direction, let the reaction force be Ry. Acceleration of the center of mass of the rod along x direction, let it be x. Along y direction, let the acceleration of the center of mass be AY, and angular acceleration of the rod, let be alpha. So, these are the assumed directions of accelerations, both linear and angular, and the direction of the reaction forces along x and y directions are also assumed. So, this is the complete free body diagram in the step 1. Next, we should go for step 2. The step 2, we have to write the equations. In step 2, let us write the force equation. The net force acting on the rod along x direction, that is Fx, is equal to mass times the acceleration of the center mass of the rod along x direction, that is x. Fx is the net force acting on the rod along x direction. Only one force is acting on the rod along x direction, that is Rx, and we have assumed the direction towards right. Therefore, Fx is equal to plus Rx I cap. Better to write all these equations as vector equations. Is equal to mass times the acceleration of the center of mass along x direction I have taken towards right or along positive x direction, that is x I cap. This gives us Rx is equal to m into x. That is equation number 1. Along y direction, the net force let be Fy, that is equal to mass times acceleration of the center of mass along y direction, that is Ay. The net force, there are two forces acting on the rod along y direction. One is the component of the reaction force, that is Ry. We have assumed its direction as up, and gravity is always acting downward. So, the net force is equal to Ry j cap plus gravity in minus j cap direction. This is the net force acting on the rod along vertical direction, is equal to mass of the rod, its acceleration I have chosen downward. You can also choose upward direction. If I have chosen downward, I have to write minus Ay j cap. So, Ry minus mg is equal to m into Ay. The equation number 2. So, force equation is over. Let us try to write the torque equation. You are writing the torque equation about the center of mass axis perpendicular to the board about positive or about z-axis. Which states that tau z is equal to Iz into alpha about the center of mass axis, which is parallel to the z axis or about this axis passing through the center of mass of the rod. The moment of inertia is equal to ml square by 12. And alpha we have assumed in clockwise sense. So here alpha can be written as minus alpha k cap. Next, to find the torque about the center of mass, the gravitational force passes through the center of mass cannot produce a torque about the center of mass, and this reaction force component Rx passes through the center of mass, it cannot produce a torque about the center of mass. These two forces Rx and mg, they pass through the center of mass, therefore they cannot produce a torque about the center of mass axis. Then the net torque is produced by this reaction force component. So net torque is equal to Ry into this length, that is L by 2, and the angle between the position vector and the force vector is 90 degree. Therefore, sin 90 is equal to 1. Then we can write the tau z direction this is R, this is R, this is the center of mass, this is the point where the force is acting. Which force? Ry. Ry is acting up. R vector and Ry vector. Bring the tails of these two vectors to a point. This vector and this vector. R cross Ry. R cross Ry. The angle is rotating or angle is moving in clockwise sense or inward direction. Therefore, it is minus k cap direction. The torque produced by this force, the torque produced by this force about this point is pointing in negative z direction or clockwise direction or minus k cap direction. In this way, you are getting Ry into L by 2 is equal to ml square by 12 into alpha, or Ry is equal to ml by 6 into alpha. This is equation number 3. So our step number 2 is over, where we mention the force equation and torque equation. Now we have to calculate how many equations we have. Equation 1, force equation along x direction. Equation 2, force equation along y direction. Equation 3, torque equation along z direction about the center of mass axis. We have 3 equations. And how many unknown quantities? We have 3 equations and How many unknown quantities? X, Ay, alpha, Rx and Ry. 3 plus 2, 5 unknown quantities, 3 equations. Therefore, we need another 2 equations. We need another 2 equations to solve. When the number of unknown quantities will be equal to number of equations, then we can solve for the unknown quantities. So, we have 3 dynamical equations. What the student do? They just add these 2 equations or any 2 equations to get another equation and name it as 4th equation, and if you add these 2, you will get another equation called 4th equation. If you add these 2 equations, you will get another equation and you can call it 5th equation. And you may argue that we have got 5th equation and there are 5 unknown quantities you can solve. It will never happen because the dynamical equations we are getting 3. Adding any 2 dynamical equations, you cannot build another 1 equation and claim that you are getting 1 equation extra. It's not like that. So, we have to apply a different concept to build the equations. The concept is kinematics of rigid body. So, we need to write the kinematical equations now. Tabulate all these equations we have obtained so far. Rx is equal to m into x, equation number 1. Then Ry is equal to m Ay plus z, equation number 2. 2 force equations, and we are getting this much from torque equation. And Ry is equal to ml by 6 into alpha. So, after writing the 3 equations, we have how many unknown quantities? Rx, Ry, X, Ay and alpha. 5 unknowns. We have 5 unknown quantities and how many equations? 3 equations. Therefore, we need another 2 equations. You cannot just add these 2 equations to build another 1 equation. It will not possible because we have applied the concept, force concept and torque concept. You cannot just add these equations and build another set of 2 equations, not possible. You have to apply a different concept called kinematics of rotation to build another 2 equations. Let us see.